Yes.
Okay. All right.
To cloud means we have to download after.
Oh, so many people are coming. So popular.
Model.
This one from next week onwards, if there is something, it will be better for me. Some stool or something. That one like that. So that I don't have to bend like that. So we'll just wait for a few minutes. Am I audible?
Yes, sir.
So can somebody else, Walter Samuel, Ikra, can somebody else respond? Am I audible?
Yes, sir.
You're able to see me? All right, very good. Are you able to share the screen or it's too difficult for you? Whatever I'm
We
writing?
cannot see, sir.
You can't
We
see?
cannot see.
It's not visible, sir.
Nothing is visible, huh? Huh?
No, it is not visible, sir.
It's too small or you're not able to see anything?
I'm not able to see anything, sir.
All right.
So maybe if your webcam has a focus option, you could twist the.
So switch off one light, sir.
Yeah, I switched off all the lights. You can see me or barely? You can't see what I'm writing. Anything is visible here?
So basically, basically it's a little bit blurred, sir. The even you are a little bit blurred right now.
Okay,
It's
so
not
then
in focus, I suppose.
No, I can't focus the. So what we do is, let's see. Suppose it is like this, you can see.
No, sir.
No. So we are doing some jugad now. Now, can you see what I'm writing? Hello?
No, sir, we are not able to see anything.
You're not
No,
seeing
sir.
anything.
No.
You're able to see me,
Yeah.
Yeah.
but you're not able to see the board. Your 9 also you can't. Let me see, change the. You can't see this also?
No, sir, it is very blurred. The camera hardware seems inefficient to capture. Yeah.
Okay, so we have to do something. Okay, so we'll do something next week. Huh? Yeah, can you mute yourselves, please? Okay, so I'll have to largely use the PowerPoint based teaching. Okay, which is okay. All right. Okay, I'll manage. Next week we'll go to that seminar room.
Similar also same distance. Sir.
Same distance. Okay. I need a 4K camera or something. So I have a 4K camera in Chennai. We wait for 2 weeks. We'll use that. Huh? All right. Okay. I want to remove the mask. Okay. Good afternoon. So welcome to this course. My name is Balaji. I'm a professor in the Department of Mechanical Engineering at IIT Madras. So I'm there from 1998 onwards. So I did my PhD in 94 from IIT Madras, basically trained in heat transfer and thermal power. MTech from IIT Madras, BE from Guindy Engineering College. I worked briefly in NIT Trichy and then National Institute of Ocean Technology at Chennai before joining IIT Madras. Since 2002, I also been working in atmospheric sciences and lately last 5-6 years also in climate sciences. So my background is conduction, convection, radiation. So I started working on all these problems for conduction, convection, radiation in engineering applications. And then I looked at radiation in the atmosphere, satellites, retrievals, geophysical retrievals, algorithms, microwave, infrared, and all that. And then I went to numerical weather prediction, then combining these two, data simulation, then climate change, and so on. Okay. Since there's heavy amount of processing of satellite radiances, inverting them, and so on, there's a lot of mathematics involved. And so we started using neural networks and algorithms, surrogate models, and all that. So a lot of optimization techniques have also been used in the last 20 years of my journey. So I started looking at optimization applicable to both heat transfer and atmospheric science. So I started a course on optimization of thermal systems in the year 2001 in IIT Madras. So about 18 times I've taught that course. Once I went to Germany for 1 year, I didn't teach it. Then last 2 years, my colleague, another Balaji, is teaching that. So heavy use of algorithms, and last 10 years, 15 years, we've also been working on what is called inverse problem, because if you look at what a doctor is doing, he's always trying to solve an inverse problem. So you go with a fever. So fever is a bad word now, of course. So you go with a fever, he or she has to figure out what is causing that because many diseases can cause the fever. So it is a classic inverse problem. The fever is the effect. What is the cause? Okay, that's what we want to know. Likewise, if a satellite is capturing radiance, top of the atmosphere radiances, then we want to know what is the condition, what is the water vapor profile, what is the distribution of cloud liquid water, what is the distribution of ice and so on in the atmosphere, which is causing this behavior. Okay, so this is a classic inverse problem. So now, since I worked in multiple areas like heat transfer, atmospheric science, optimization, inverse, and so on, and now last 5-6 years, everybody's talking about data science, data and all that. We have been using that without using this term data science. So I thought I will use this time now I'm on a sabbatical year from January to June. So I'm sitting in D303. If you have some doubts in optimization and you want to discuss something on climate change and algorithms or data science, feel free to walk into my office. So I thought I'll give a short course where I want to demystify this data science, because non-computer science people are always, I feel they're getting threatened with this big data analytics and all that. So the first few lectures will be very basic. I want to, this is basically a 101, okay, 101 course on what is data science and so on. And then we'll go to the math a little later on. All right. So I will use, yeah. Are you able to see the screen now? I'm sharing the screen. Hello.
Yes, sir.
Yes, very good.
Yes, sir. Yes, sir.
Yes, sir, we are able to see.
Yeah. Okay, I have a tendency to speak fast. Okay, because that is a state of my mind. Anyway, we are recording it. Try to follow as much as possible. If something is really bothering you, stop me. I'll try to explain it again. Otherwise, what we'll do is we will have a Google. What is that, Girish? What is it called? We'll have a place in the cloud where we'll put all these lectures. All right. So you'll be able to access them leisurely, and you can go over this again and again if there are certain things which you did not understand, or you felt like you did not understand, or what have you. Okay, so I've titled this short course as Data-Driven Methods and Machine Learning in Atmospheric Sciences. All right. So the course objective is basically, if you look at it, now there's a lot of availability of high resolution data in atmospheric science, both measured data and from models. There is a plenty of data in all the fields, medical field. Okay, if you look at even your Amazon, your Flipkart, every time you're doing a Google search and so on, lot of data, you're looking at a lot of data is also being generated about you, your spending habits, which one you are watching. Okay, Netflix or Amazon, what kind of movies are you watching, all this. So somebody is constantly taking this data. Okay, what they will do with that, we don't know. Now, there is a tremendous scope for developing a data-centric model, which is a completely data-driven model. Okay, or approach with a view to accomplish the following. Okay, so let us see one way of the most popular way of doing science is basically it is the empirical method in science. Okay, so what we do is we do some experiments. We basically looking at phenomena. Okay, we do a lot of experiments. We collect some data. Then what we do is we try to theorize this or try to develop a theory based on first principles modeling. Okay, we try to do a first principles model. Okay, apple is falling down. Okay, so it can be characterized by an initial position. It can be characterized by a position vector. It can be characterized by a displacement. It can be characterized by a velocity. It can be characterized by an acceleration. And then you say, let us say, okay, what are the forces acting on this? Okay, then Newton's second law of motion. So you try to bring in all this, and then you try to theorize and try to explain. You try to analyze with a view to understand. Okay, you want to understand phenomena. You want to understand the material world. This has been the classical approach to doing science. Of course, there's one more way of doing science where it is axiomatic. Okay, where is you state some theorems. You just state some. You start with some lemma or a theorem, and then you go about proving that. Okay, so it can be observation driven, or it can be just you start with a postulate or a theorem, and then axiomatic. It's very axiomatic. Okay, so that is another way of doing science. Now, if you come to this empirical method, now what is data science? What is data science approaches? When there's a lot of data, there is no need to always look at a differential equation or an integral equation or an integral differential equation. There could be other ways of doing science. Okay, if there is a lot of data, can we look at alternate ways or alternative methods or alternative approaches to making sense of the data instead of always trying to find out, write the equation as d squared by dx squared plus blah 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 d squared, whatever. You write it as a partial differential equation, ordinary differential. This is a very Newtonian approach which I have been using for hundreds of years. Now this approach is being threatened by the invasion of data. This data could be generated by the solution of the equations themselves, or it could be just the MRI data or a CT scan data of so many patients. Okay, Professor Parmesh is also there in the audience. So we can, in fact, you must have seen a lot of X-rays, a lot of CT scans, HRCT, okay, high resolution computerized axial tomography of the lungs, which has become unfortunately so popular during the COVID times. Okay, each of this gives a signature. It gives a signature about what is going on in the lungs, what is going on in whether there's a COVID pneumonia, what is happening in the lungs, and so on. All right. So from this data, can you all, if you are able to do a clinical correlation, okay, and you set out what is the input and what is the output, can you make sense of this data? And then it's not that we want to replace the doctor. So can it help doctors to make better decisions? Okay, so that it leads to better treatment options, or can you Or the next level would be, can you take a digital X-ray and then see the correlation between a digital X-ray and the HRCT, and then now say, because HRCT is so expensive and many people cannot afford, and sometimes it's not required because so many X-rays, it's built up of so many X-rays and it's taken in several 2D positions, and there's a three-dimensional reconstruction of the whole thing. Now, can somebody extrapolate from a 2D image to a 3D image so that it's just 150 rupees, 200 rupees, whatever of your X-ray? Can you tell some story about what is likely to be the picture in HRCT if somebody is undergoing COVID pneumonia, for example? So data science may have answers to this. Okay, so and then we'll have to validate this and so on. Okay, let's move on. So there is a tremendous scope for a data-centric modular approach with a view to accomplish the following. What is that? Development of very quick surrogate models. Development of very quick surrogate model means there is a replacement. There is a replacement model. Surrogate is a replacement. Okay, so it is so expectedly the surrogate will be very fast and efficient. A neural network can do something in 1,000th or 1 by 10 to the power of 4 times what a regular equation will do. But again, you will ask me, see, for developing the neural network, a lot of work is required. Yes, a lot of work is required. But the data need not be solved. Data need not be obtained only through a neural network, through the solution to the equations. The data can come from a hospital. The data can come from your Fitbit. The data can come from your Apple Watch. The data can come from the user accounts of Amazon, of all the users and so on. All right. So if plenty of data is available, is a differential equation the only way to do science? So that is the fundamental question. That's where they are shaking us. That's why where all of us, we are highly mathematically trained. You have a particular way of doing science. It unsettles us. This whole idea of data science seems to be threatening us. Okay. So there's a saying in English, if you cannot beat them, join them. Okay. So if you cannot beat it, let's join the bandwagon. So let's also have some fun. So let's see what this data science is all about. So we'll demystify this in 12 hours or so. And then you see how you can apply it in your actual problem, be it health sciences, be it geosciences, be it atmospheric sciences, climate sciences, engineering sciences, thermal sciences, environmental sciences, and so on. Okay. So let's get back to this. So there's a tremendous scope for a data-centric modular approach with a view to accomplish the following. Development of very quick surrogate models, development of algorithms to retrieve geophysical parameters. For example, 70% of the Earth's surface is oceans. You can't directly measure rainfall from the ocean. So now the important engineering question that has to be asked is, can you remotely measure rain? Yes. So then for example, that question itself is like paradoxical or illogical. How can you measure remotely? So okay, let's change the verb. Let's say that I won't measure, I will estimate. Okay, I will estimate the rainfall. How do you estimate the rainfall? From the sea, you know there is a temperature and emissivity of the sea. There is a radiation which is coming out from the sea. Have some instrument on the top of a satellite. Now, takes two situations. There is a big cyclonic storm in the bay. What will be the intensity of the radiation which is picked up by the satellite? That is situation A. Situation B, there is a very clear sky. Now, what will be the information which is picked up by the satellite? There is a whale of a difference between these two. Therefore, can you characterize this? Then you go into radiative transfer models. What are the parameters in this model? Now, if there are a lot of satellite pictures, can you turn around and say satellite pictures or satellite images or satellite data, radiances, whatever? Okay. If your internet is on. Am I still audible? Hello?
Yes, sir.
Sir, it seems like you're having some bandwidth issues at your end, but otherwise we're able to hear you.
No, it should be okay. The internet is, I'm not able to use the campus internet because I'm using my dongle, but you're able to see the slides also, right? Huh? Are you able to see the slides? Hello?
Yes, sir.
Yeah,
Yes,
yeah.
sir.
Okay. So development of estimate. Okay, so now coming back to the rainfall problem, can you? So now that's a big science. So you have to see rainfall in you're measuring the microwave intensity. What will be the frequency? That frequency. Then you have to be a scientist. You'll see what are the whether microwave can penetrate the clouds, whereas infrared cannot penetrate the clouds. What will be the frequency? You have to look at ice scattering. You have to look at water droplets, how they scatter. Is it a spherical particle, non-spherical particle? That's a big science. So you have to go through that. You have to go through that steep learning curve 4-5 years before you start doing something. All right. There is a data-driven approach. If you've got a lot of satellite images and simultaneously using a ship or something or somewhere you have a measurement of rainfall, then input as a directly you correlate. Or what you do is you have a lot of measurements over the land. Over the land, when you have a satellite picture or satellite images, or why satellite images? Satellite observations. Now, can you try to turn around and say that this will be the rainfall? If this is what the satellite is picking up. This is the rainfall, and then that is already like ground truth. You've got rain gauge data or whatever, or from another satellite derived algorithm, you've got a cross correlation. You do this, and then you say you can extrapolate it to the ocean. So therefore, what I told you before, the 3 minutes back, that high science of understanding radiation, understanding all the things in the integral differential equation, and then figuring out all that, writing a code, whether in Fortran, MATLAB, Python, R, whatever, is that required? So can we beat it? So that is a question they're trying to, if you have too much of data, maybe it is possible to beat it in some other situation. That's the whole idea of data science. Okay, the third would be development of estimation prediction algorithms by employing machine learning algorithm. Neural network is one. What is this neural network basically? Okay, so it's basically one way of looking at it is trying to mimic the biological processes in the brain. Okay, for example, just outside the MS Ramaya, you want to cross the road. Okay, you're a pedestrian. So what is the basic rule? You'll go and stand in front of the zebra crossing, and you'll just see whether what is that? It shows green for the pedestrian. Then you cross once. Very nice. You come back. You finish your shopping and come. It shows green for the pedestrian. You cross. One auto rickshaw fellow comes and hits you from the left side. What happened to your neural network? Wow. Now you figure out that is ideal situation. This is India. Okay. Regardless of whether it is green or whatever, that is only a necessary condition mathematically. It is not a sufficient condition. So you train your neural network. What is the additional input you are getting parameter? I will see first whether the signal is green. Then I will see left side or right side whether any car, auto rickshaw, anything is coming. And then I will also see what is the width of the road and whether today my legs are okay, I'm able to do this thing, my chappal is okay, my shoes are okay, I'm fine, I'm not carrying too much weight. Then you do an estimate. Now this is like 80 feet road. Can I cross this 80 feet road in this many number of seconds or whatever? So this is how you continuously get trained. Okay, this is a simple neural. So we do this all the time. But finally, the decision is only two, right? It is binary decision. I either cross the road or do not cross the road. There is nothing like I go and stop at 1/4 of the road. I'll go and stop at 3/4. There is nothing like that. You do it or so this binary. But so the output is binary. What is that? It is basically yes or no. What is that yes or no? Yes or no crossing the road. Like that, you can, even in engineering and science, you can have inputs and outputs. Output need not be binary. So the output could be the rainfall. The output could be the expected, Dr. Parmesh can correct me if I'm wrong, the expected severity of the COVID pneumonia based on some cheating we do. Based on X-ray itself, I will tell. I don't know whether it's possible at all. I'm just, maybe I'm just jumping the gun or I'm too ambitious. If you're able to do that, so based on a data science, then it will be a low cost approach to that. All right. So, all right. This short introductory course aims to present an overview of the key concepts involved in the above, with examples drawn from science and engineering in general and atmospheric science in particular. Because I wanted to let the general audience enjoy this. So the atmospheric science examples will come towards the end. But because the subject matter is so general, you can apply it to any field. Prerequisites, I don't expect any prerequisite except for basics of college level probability and statistics. I'll try to keep them as simple as possible. Who can attend? Scholars, students, project staff with an interest in machine learning and data driven. This is what I've written. Module 1 will be introduction to data driven methods and machine learning. That will be today. and then description of errors and so on. Then the module 2, I will introduce you to some high math. And so that will be basically an estimation. Treating the estimation problem is an optimization problem. And then there are two types of estimations. One is parameter estimation, where you estimate a parameter, or like rainfall, or a function estimation. You say something like a plus bx, a plus bt, or a e the minus bt, or whatever, exponential, logistic, whatever be your functional form, the constants and the exponents of the parameters that you want to figure out. Then least square regression, and then I will teach you some Liebenberg algorithm and so on, Markov algorithm. All right, module 3 is basically, is a very important thing, is basically the Bayesian framework. The Bayesian concept is basically this: if you approach any engineering problem as different from approaching it purely mathematically, is we generally have an engineering sense of it. We have an idea of where the parameter, the bounds are going to lie. This is called prior information or prior knowledge. So this is basically belief. Okay, this is belief. What is this belief? What is the idea about what you are trying to seek, even before you are solving a model, or even before you are making the measurement? What is the prior belief you have? Okay, I have so many beliefs. So how does it help in an estimation problem in data science? What I will do is I will quantify these beliefs. How do you quantify? Either there can be a point quantification, or I will quantify them in a probabilistic sense. I'll quantify them through a Gaussian or Poisson distribution or a Weibull distribution, whatever. All right, so we will look at this, and then how to sample the space and so on. That is the module 3. Module 4, I will teach basically neural networks, that is machine learning. Module 4, about 2 to 3 lectures, and the final lecture will be finally the summum bonum will be basically my students, what all they have done using neural network in the last 5 to 10 years. I'll try to give a capsule or essence of it. Okay, how I have used it in my research career. So this will give you a general flavor of how you can possibly use it in your field. Okay, in your problem of interest. So today is the start date. So we'll do 4:30 to 5:30 every Tuesday, unless there is some other engagement or something, in which case I will give a prior notice 1 week in advance, or sometimes we can, it may extend up to 5:40 or 6 or whatever. I'll tell you in advance. Okay, so this is the meeting link. So all right, okay, so lecture 1 is basically introduction to data science. What is data science? Okay, am I still there? I am seeing only my presentation. Tejal, am I still there? Hello? Hello?
We can hear you, sir.
Yeah, but I have no way of finding out whether you're hearing me or not. So that is a problem with the online class. My friend, the present dean of students, he took a full class of 1 hour in 2020 in IIT on a course. He figured out that last 45 minutes the internet was not there, and no student told him. Okay, no student called him or told him, and then, but the good thing is he recorded it, so that of course he fired a few students afterwards and all that, asked them why you didn't tell me and all that. Okay, Girish, are you there? Girish Kumar, some students from IIT are also joining because they are pros in
Yes, sir. Yes, I'm here, sir.
Zoom. They have helped me in the last 2 years. So Girish, if there is any problem, you give me a call. Okay.
Yeah, sure, sir.
Sir, you're not visible, you're not audible, whatever. Okay. What is data science? First, what is data? What is science? We'll combine these two. That is data science. Dictionaries define data as a plural form of datum. Datum being something given or admitted, especially as a basis for reasoning or inference. Okay. These Girish, there is a typo. Okay. Something given or admitted, especially as a basis for reasoning or inference. Okay. So, all right. It says it constantly wants me. My internet is unstable. Okay. So for practical purposes, data can be considered as both plural and singular. Let's not make this fussy distinction. Now consider a table containing the ages and grade point average obtained of some final year students in, say, in my IIT class. Okay. Now let us say that Okay, I have to go to slideshow now, no? Hey, Girish, is it okay? Hello? Hello?
It is
Yes,
fine,
sir. It's
sir.
fine,
It
sir.
is appearing fine.
Yeah. Now, Rahul, Sai and Surat, Priya,
fine,
let
sir.
us say 18 years and 10 months, 19 years. So basically it is a name, age, and what they have scored, maximum out of 10. Okay. For example, Rahul. Rahul could be datum, but Rahul could also be a data. Rahul is a boy, Rahul is a student, whatever. Okay. And so 18 years and 10 months is a datum, or 18 years, 10 months is also data. Rahul CGPA is 7.8, that is also data. So this is a lot of data because 4 students, 4 ages, 4 CGPA and all that. Okay. Now don't try to do a neural network and try to correlate age with CGPA. That may not work. Okay. So don't. This is just a very simple, plain, vanilla example where I just showed you that there is something. This is what is data and what is datum. Okay. Okay. What is science? According to the Oxford Dictionary, science is a systematic study of the structure and behavior of the physical and natural world. I come again. It is a systematic study of the structure and behavior of the physical and natural world, the material world, the outside world. If you study about yourself, self in capital, that is a spiritual world. Okay. So now we are looking at phenomena. We are trying to understand the world with a view to master it so that we can make our lives more productive, more comfortable, whatever. Okay. Technology, development, whatever. So science is a systematic study of this. Now I have given you the definition of data. I have given you the definition of science. Let's combine these two. So in view of the above definition, data science can be defined as follows. Data science is a field of study and practice that involves the collection, storage, and processing of data in order to derive important insights into a problem or phenomena. Please note that data science is the first field of study and practice. Not only field of study, it's practice. What does it involve? Collection, storage, and processing of data. It doesn't stop there. You collect, store, and process data. What is the purpose? In order to derive important insights into a problem or phenomenon. Okay, so it involves several steps: data collection, data storage, data processing, and finally you have to get important insights into a problem or a phenomenon. Okay, how are these data generated? Data can be generated either by human beings or by machines. Okay, you may say, sir, animals also generate. Yes, if you're interested in studying animals, there is a Professor Sukumar from Ecological Sciences. All his life he studied elephants. Okay, so you can get you can get data from animals also. So okay, pardon me if I mean that I'm not included there. Generally, data can be generated by humans. How by humans? You can do surveys, you can do logs, you can questionnaire. Now, if you go to the Indigo, if you buy a ticket in Indigo, by default, it will say 10, it will give 10 star out of 10 star. You say, thanks for rating us. You wouldn't have done anything. So when you go to a service center now, sir, review will come, sir. You give me 5 stars, sir. Yeah, all of you have seen this, no? Because their bonus or their incentive is based on the feedback. Okay, so the feedback is also game nowadays. All right, be that as it may. You can humans generate data through multiple ways: surveys, logs, questionnaires. Sir, I'm also generating data, sir. Our students our friends in this building will say, sir, I'm also generating lot of predictions of atmospheric data, of aerosol. But friends, hang on, that is not generated by you, that is generated by machines. Okay, these machines can either be the instruments or the computers. All right, you are a big party to you are responsible for making them work and all that. But finally, it is generated by some machine or a computer. By machines, weather data, climate data, pollution data, consumers buying preferences from say Amazon, traffic data from cameras. Okay, hospital data. So many data are there. Okay. What can be the forms of the data? The data can be in text form. The data can be in audio form. The data can be in video form. Okay, it can be in the form of numbers. Data can be in several forms and formats. Why this big hue and cry? Why is data science so important now? According to Chirag Shah, I followed his book for the introductory lectures. He's a professor in University of Washington in Seattle. So according to Shaw, 3 V's are the reasons for the explosive growth of data science. Velocity, volume, and variety. Velocity, the speed at which data is accumulated, amazing that they, okay. The size and scope of the data, the volume of the data, okay. 3, the massive array of data and types, structured and unstructured, which is available in the world, and the growth. Each of these V's has dramatically increased in the recent years. For example, even your desktop has more than 1 terabyte. We all started with 256 kilobyte, man. We started with monochrome green monitor in the 80s, in the late 80s when I was in college, finally a project. 286, 386, and 486. These were the machines. Okay, monochrome monitor. Okay, now you see, a mobile phone can do so much. All right. If each person, this one some projection, if each person in the world has 5 TB of data with him or her, and with a population of 8 billion, the world has a population of 8 billion, maybe more. The total data volume is expected to be 4 zettabytes, 40 zettabytes. 1 zettabyte is about whatever, 40 zettabytes. So you can see that it's going crazy. There's so much of, therefore, in order to store this data, you need server. So there is a lot of energy consumption. I think a few percentage points of whatever power is generated by all sources in the world is for maintaining this service at a particular temperature. Therefore, as a thermal engineer, my students can also please note in thermal sciences, data center cooling and data center thermal management is a very important topic of research. It's likely going to be a multi-billion dollar. Okay, all right. What are the applications of data science? Okay, something is coming here. Finance. Financial data scientists capture and analyze new sources of data, stock market data, build predictive models, and run real-time simulations of market events. They will look at what is happening in Singapore, what is happening in Frankfurt, what is happening in London, New York Stock Exchange, Sensex, where to invest, okay, all this, all right. So then the lending rate, the prime lending, the PLR, and this thing and all that, right? So finance is there's so much of data science in finance. It can also be used in trend detection and risk reduction, okay. For example, just through the mobile number and PAN number of an individual spending pattern. So if you give the mobile, so there's something called a credit score, right? CIBIL rating. I don't know if you've taken a loan. There's a CIBIL. There's something called CIBIL rating which is worked out. There is a number which they give that tells you the story of what are the past loans you've taken, how they've repaid, whether you have defaulted, and so on. So somebody's credit, so it's all based on data like that. All these finance companies, all these banks have got access to all this data. Okay, so if you just put your PAN or it will tell a lot of stories about your financial health. Okay, and if you just see the CoWIN website, the CoWIN, okay, so 160 crore vaccinations have been done. Then minutes after you're vaccinated, automatically something comes on your mobile. So this much of data, some server is storing it, and it is doing it almost without mistake free. It's a big achievement. The railway reservation network, India railway reservation network is one of the largest in the world. I think the CoWIN is even overtaken that. I mean, it's bulletproof. It tells you, it even tells the name of the nurse who administered that injection to you, right? Okay. Now, healthcare. Okay. Consider the thousands of scans of X-rays, CT, MRI available to your hospital department or even to government. Okay. So there's a plethora of data available. Clinical correlation, but however, first clinical correlation is required. Okay. Okay. For example, in the case of nowadays it has become fancy. Once somebody is having COVID, RT-PCR positive, then they are triaged. Okay, mild, asymptomatic and mild, that is one case. Then moderate and severe infection. So they will say RR, respiratory rate less than 12, between 12 and 24, greater than 24, oxygen saturation under room air 94, less than 94, less whatever. Okay, based on all this, you're triaged, and then you're assigned to either home quarantine or this thing and so on. Then during this they will take some tests. Okay, IL-6, CRP, ESR, so many tests, the D-dimer and all that. So some of these are not direct. If something else is going on in the body also, some of these parameters can increase. Okay. For example, somebody is having a cancer or something, that a D dimer could possibly increase. So only a doctor will know. Suppose something is high or low, then they have to first correlate it whether it is correlating with the present condition or not. That's why data science by itself could be dumb. Okay. That consciousness for it, the consciousness for it has to come from some expert. So the domain knowledge. Okay. So what the idea of this course is, since all of you are smart people and you're all having hopefully having good grasp over your domain, just master this data science also, then you'll become king. Okay. So your area plus data science is a deadly combination. So it will take you places. That is the idea of offering this course. All right. Now let's get back to this. If you have so many X-ray, CT scans, MRI, now the clinical correlation of these two disease outcomes can be used effectively in telemedicine. Okay. Also, you can study the progression of a disease. You can study the progression of a disease or a pandemic for a large number of patients. For a large number of patients, it is seen. It is seen. Okay, that the WBC is so much, or this is so much, and it is correlating like this. The ESR is so much, and if ESR or this thing or D dimer has to be taken on the 4th day, 6th day, 7th day, all the doctors will sit and will say that, and then there's a protocol. Then the protocol will be developed. So this is all data driven. Okay. Now this Sutra model and all that, this is a completely data driven model with some model parameters which are based on last week's projections or the previous week's projections, so on and so on. So they run what is called a population dynamics model to estimate the number of cases. Okay. And what is a peak? What is the peak of the corona means? What is that question? The peak is what? There could be several peaks. Okay. What are you talking about? The peak of the actual number of cases. That means every day it is fluctuating. So there could be a peak of the actual number of cases, number one. A peak of the daily average of the last 7 days, because the 7-day moving average of the case. A peak of the active cases, peak of the hospitalization, peak of the death, whatever. So there could be several peaks. Okay. What is the peak you are talking about? When do you declare that the pandemic is explosively growing, or the pandemic is receding, or it is becoming endemic, and so on? So suppose somebody is RT-PCR completely asymptomatic. What do you do with that kind of data? Okay, so all these things only medical professionals will be able to. A lot of data is there, so they'll be able to tell us properly. All right. Now let's come to the another aspect in healthcare. All of us, I also wear this smartwatch. The role of smartwatches cannot be underestimated. It has given confidence to many people. Okay, they give so much data to every individual about their exercise and sleeping habits, the calories burned, not the reading, the resting heart rate. Okay. Okay, so it is, I'll correct this. Huh? The rest, I will save it. Huh? Oh, it went to Rahul. Sorry, sir. What happened? I think I touched something. Okay, all right. Okay, the role of smartwatches. Okay, so resting heart rate and so on. Now I think you also have that SpO2 is a fancy parameter now, right? So there are also watches which give the SpO2 and all that. Okay, all right. Now, application of data science in atmospheric and climate sciences. These are very data-rich fields. Okay, a lot of data is generated in atmospheric and climate sciences. So it is very important that people who are doing their projects or masters, PhD, whatever, postdoc, whatever your career is in this field, you better understand how to optimally use data and how you can enrich yourself and your career by understanding data science. Okay, plethora of data is available from both models and observations. Okay, so we have to scientifically handle this. So there are plenty of ways in which data can be used. The first and foremost, simplest is making sense of the data and performing trend analysis. Then building a predictive model that is completely data driven. Okay. Now let's see some applications of data science for you guys, atmospheric and climate scientists. Annual loss of mass for a glacier. A lot of data is there. Can you develop a neural network, machine learning? Can you do something so that you can predict? Accurate estimation of rain from radar reflectivity. The radar is basically sending out some signals. Okay. Now, if there is a rain, then there is a reflection. If there is no rain, no signal will come back. So depending upon what you receive, the reflectivity from the radar has a strong signature with the rain. Okay, so this is the fundamental principle. Then you go to Marshall-Palmer distribution, blah 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 blah, all that calibration, validation, all that. Okay, the first is what is the principle? What is the underlying principle behind this? Prediction of a storm based on observations from satellite or radar. You try to locate the eye of the storm from based on the satellite and last 6 hours and 12 hours. From that, can you tell for the next 6 hours or 8 hours? So this is called nowcasting. So you can actually do that, okay, using satellite or radar data. Building surrogate or fast models for infrared microwave radiation in the atmosphere. Building fast models for accurately tracking the storm movement, okay, for accurately predicting the storm surge, okay, at the time of landfall. Then AI, ML, artificial intelligence, machine learning driven short-term predictions of monsoons, prediction of extreme events, mesoscale connective systems, and so on. This gives a overall, this is just a sample of the possible applications of data science in climate and atmospheric sciences. Data science, and what is the relationship between data science and other fields? Data science and statistics. Some people, the hardcore statisticians, say that it is just statistics. It's like old wine and new bottle. It is statistics which is repackaged. Okay, it can also be true, but there are some key differences. Agreed, statistics and data science are closely related. Sangamesh, am I audible? Sangamesh?
Yes, sir. You are audible, sir.
Yes, sir.
Okay.
Audible, sir. You are audible. Audible, sir.
Okay.
I can hear you.
So what is the relationship between data science and other fields? Data science, statistics, these are closely related, but some argue that data science is nothing but statistics in a new avatar or avatar. Be that as it may, there is a key difference. Statistics was developed before the computer came in. Therefore, statistics technically belongs to a pre-computer era. Okay. Of course, some people can come with something, some weapons and kill me if I say this, because computational statistics has become a very important field now. There are a lot of statisticians who heavily use the computer, but that came later. Originally in your statistics book, mean, standard deviation, kurtosis, histogram, all that. Where was the computer? You studied in your 9th class or 10th class. I studied in my 9th class, which was like 40 years back. Okay, so 35, 40 years back. So the statistics belongs to a pre-computer era. Okay, pardon me, don't hang me if some statisticians don't like what I've said. Often statistics help in fields like quality control, statistical quality control. You just say that some company is making nuts and bolts. Every 1 hour, they are making 1,000 bolts. I take 10 bolts and check the dimensions. If it is okay, that is called a sample. If that sample is okay, then that whole lot can be cleared. So this is called SQC, statistical quality control. Sample testing, market surveys, and so on. So statistically, now you want to do corona testing. What will you do? Random testing, or you will go and simply go to bus stand and railway station and people without symptoms also you will test? Or how will you test? How will you go about? Because the kits are expensive and we don't have millions and millions of kits. So there should be a scientific rationale. Okay, even if you want to, you got that thing to test. You want to test. Who will you test, and what is the scientific rationale? Okay, so some statistical concepts are required. Okay, data science on the other hand is the latest field. It is a 21st century field dealing with data problems of this century. That is the first difference between data science and statistics. Hence, data science is concerned with large volumes of data. That's what is called big data. Big data. Lot of data is big. Don't get scared if somebody says big data. Atmospheric and climate science, health science, they are having the biggest data. If somebody says big data, you don't get worried. You say, Are Baba, I also know what is big data. I also handle big data. Don't get unsettled when somebody says this. Okay. Hence, data science concerned with dealing large volumes of big data, harvesting data. Sometimes some missing data will be there. Some data without integrity will be there. So you should know about harvesting the data, collecting the data, cleaning up the data, solving whatever you wanted to do with machine learning, whatever, and post-processing them. So fortunately or unfortunately, computer literacy holds the key to be a successful data. If you are just good in mathematics, it is not enough. You have to be good with computers. So which means either you are a good programmer, or you know how to use MATLAB, Python, R, or whatever. So the first level of data science you can manage with Microsoft Excel itself, but it will take you only to a certain level. If you want to go to the next level, you have to be computer literate. So, but if you want to be a statistician, you could have managed without big computers. All right. Okay. Relationship between data science and other fields is continued. According to statistician Yang, data scientists need to have the following 3 important skills. First, a strong knowledge of basic statistics and machine learning. Why is it required? Because it should be enough to avoid extrapolating results from a small sample size. Okay, particularly in the field of psephology, you cannot take sample voters from one district and say that India will vote like this, right? There will be a lot of, there are regional biases, language biases, some religion will be more represented in one region, caste, many factors. So how a cephalogist? A cephalogist is somebody who scientifically studies election trends and so on. So how do you choose a sample in your election survey? Okay, in your not the exit poll. Exit poll may be reasonably all. Exit poll also you cannot. Somebody will vote for X party and he will come and tell I voted for Y party. So that is a okay. That is a data with infidelity. That data has to be removed. So how do you know somebody is telling the truth? And regional representation, all that. So it is a very, that's why often models go wrong. Often models go wrong in this. All right. So you should be smart enough to avoid extrapolating results from a small sample size, collecting a small sample and talking about big things. Number 1. Number 2, you should not misinterpret correlation for causation. I was talking to Professor Paramesh, the other class. Professor Paramesh, are you there, sir? The audience? Hello? Dr. Paramesh, are you there? All right. So, for example, if you look at...
I'm here, sir.
Okay, sir. Thank you, sir. Okay. I was just telling him, suppose
Yes,
you look at the data of last 40 years, professor salaries, and last 40 years alcohol consumption, both will rise. Now you are a big data scientist. You are a big data scientist. You just correlate and say that all professors started getting more money, so they started drinking more. So you develop a theory for that. Okay. Hopefully the theory is false. Okay. Hopefully. Okay. So the difference between correlation and causation is the first thing you have to learn as a data scientist. Don't get carried away just by data or correlation. Correlation does not imply causation. Causation has to come from somewhere else. So causation has to come from your strong subject knowledge, from your domain, from your practical experience. That is why, regardless of all this data, whatever it is, finally based on the see, some doctors will say, sir, you will say clearly, if you give a lot of reports to the doctor, a very experienced doctor, what he will say, no? Sir, I cannot treat the report. I have to treat only the patient. Report may say so many things. How are you feeling? What? First, you have to talk, right? You have to talk to the, you have to tell them what is the report may say so many things. We don't know the default. They will say that pulse oximeter always shows 94, 93. We don't know that person's default may be 92 or 93. So what will be the first? So a better condition would be compared to your normal value. If it goes below by 3 points or 4 points, that may be more scientific. But what is a normal value? Because 2 years back, nobody knew pulse oximeter is done only in emergency ER room or pre-surgery where you're admitted. Who knows about pulse oximeter? Now it has come to medical shop. It has come everywhere, right? So, and also they say your pulse rate is more. And what is my basic pulse rate? What is my resting heart rate? We don't know. So when you don't know your baseline values, that report, once you do a test, some 4 parameters will not be all right. All right. That is why a doctor is required. So doctor will, so he'll be able to separate the noise from the data. He'll be based on your symptoms, based on his physical examination and talking to you. He or she will be able to tell what is the correlation, which are the parameters which are important, which are the parameters which are not important. Okay, right. Now, first thing, so you should have a knowledge of basic statistics and machine learning. Second, some computer science skills are required and knowledge of programming language like Python or MATLAB. If you want to do just basic data science, be an expert in MS Excel or something, that will also be fine with you. The ability to visualize and express data in the form of color plots, histograms, pie charts, distributions, okay? And based on this, you do an analysis. So in a way, which is meaningful even to the uninitiated, somebody who is not an expert in the subject also using this data analysis, you should be able to explain to him or her. There's no point in saying this is hi-fi, I'm hi-fi, you won't understand this. Okay, we should never do that. So if you have to be a successful data scientist based on your data, whatever you did with your data, the churning and all that, you did all that masala with your data. Finally, what is analysis? Can you make a layman understand? Can you make a layman understand? Okay. Okay. What is the relationship between data science and engineering? Nowadays, almost all fields of engineering have created a demand for data scientists and data science methods. Okay. So high-rise buildings and all that, for example, the construction of now Noida, there is a big airport, Uttar Pradesh is doing. The use of drones in monitoring the construction of a building and all that, huge volumes of data need to be analyzed for making choice of construction design in activity. So such big building, drones can be very effectively used, and drones will give pictures and this thing, they'll give a lot of data. So as a civil engineer or as an architect or a structural engineer, how do you make use of this data? So this is basically big data in civil engineering. Consider the structural health monitoring. There are cracks in a pipeline. There are cracks in an aircraft. They should not be serious. Suppose there are cracks. You want to do a structural health monitoring remotely. So you will say, probably you will send ultrasonic waves. And then if the surface doesn't have a crack, it will give one signature. If it has a small crack, it may give one signature. If it has large cracks, it will give a completely different signature. Okay. So this can be used for health monitoring of pipeline, aircrafts, petrochemical plants, power plants. So this is a separate field called non-destructive testing, NDT, where heavy use of data is there, heavy use of data. So you have to develop algorithms for fault detection and so on. All right. Remote measurements are often made of potential cracks. Large volumes of data are to be analyzed. In thermal sciences and fluid flows, now my colleague, another Balaji in IIT Madras, is working on what is called physics-informed neural network, which is an alternative to solving the original differential equation by using some finite difference, finite volume, and so on. So this requires a very good knowledge of data science. Okay. Now, the first thing to be a good data scientist is computational thinking. I'll just give this example and then I'll close with this. It's already 5:20. This will take about 5 to 10 minutes. We'll look at this example. Okay. I'll tell you what computational thinking is, and then we look at this example. This computational thinking is becoming an essential skill, particularly for data scientists. According to Wang, computational thinking is the use of abstraction and decomposition when attacking a large complex task or designing a large complex system. I come again. What is computational thinking? It is a use of abstraction and decomposition. Abstraction means first theorizing, and then decomposition is breaking down a big problem into sub-problems. This is very much required for attacking a large complex task or designing a large complex system. So the computational thinking is an iterative process. That means trial and error. You will do trial and error based on the following 3 stages. First, you will formulate the problem, that is abstraction. Second, you will express the solution, okay, animation. Third, the solution execution and the evaluation, you will finally do an analysis. Okay. Now I'll give a very simple example. Okay. Consider a bunch of 10 numbers. Let me drink some water. Consider a bunch of 8 numbers. Okay. 8, 23. What are these numbers? It's obstructing. What did I write there? 8, 23, 13. Correct. 5, 29, 37, 56, 2, 98, and 42. Girish, I'm still there, right?
Yes,
Yes,
sir.
sir.
All right. Now, using a systematic approach, find the largest of. Okay. Now, what you do? Hey, what is this, sir? Simple problem. This is LKG level problem, you'll say. Now, the idea is this whole idea of abstraction. So what will you do if you have 1,000 numbers? Can you just see like this? Now you can scan. You can scan and say, sir, 98 is the biggest number. But if I give you 5,000 numbers, how will you do that? So that is why a systematic approach is required. So that systematic approach is computational thinking. Now what we can do now? Instead of looking at all the numbers and getting confused, let us take the first two numbers, 8 and 23. Which is bigger? 23. Okay, now I ditch the 8. So I choose 23. Now the next two numbers, 23 and 13. Now between this 23 is bigger. I'll go to 23. The next two numbers, 23 and 5. Choose 23. Now again I go to 23 and 29. 29 is bigger. I ditch 23. Like that when I go, I'll figure out that 98 is the answer to this problem. If you continue the process until we have seen all the remaining numbers, then we'll end up with 98 as the largest. Okay, and this is our solution. So instead of looking at like this, scanning and saying 98 is the answer, the funda or the idea of taking two numbers at a time, eliminating one of the numbers, and then going to the next number such that you have exhausted all the numbers in the series. It is a fail-proof. It is a fail-proof, systematic, boring though, but it's a systematic, fail-proof, pakka scientific approach to finding the largest of these 10 numbers. So this is computational thinking. This is what the computer scientists will do. We are not computational scientists. Therefore, if you have to become a good data scientist, we should also think like that. There's a system. What is a systematic approach? It should work for 10 numbers, 1,000 numbers, million numbers also it should work out. Then it will come, the next stage would be how to develop an efficient algorithm. First, an algorithm which works. Okay, they'll always say a machine which works is much better than a machine which does not work. Among all the machines that work, you just try to choose a machine which works better. That comes later. So optimization comes later. First, you want a workable or a working system. So you need a workable algorithm. So this is a two at a time, eliminate and then proceed. So this is the basic solution to the problem. Now, this is a very simple example. Nah? What did we actually do? We broke down the problem of studying the largest number in an array consisting of 10 numbers into a set of small problems. Each small problem comprises only two numbers at a time. That is the decomposition. That is the decomposition in computational thinking. More importantly, a process was derived by which two numbers at a time you compare. This could be applied to 100, 1000 or 1 million numbers. So if you can scale it up, if you can extrapolate it to any number of numbers, this is the abstraction and generalization. This is at the heart of computer science. This is at the heart of data science. This is at the heart of computational thinking. So the above is a clear example of computational thinking. Now take home exercise, extend this problem to sort all the 10 numbers in the descending order. Okay, now I close the presentation. Now, can somebody tell me how to proceed? How do you descend? In computational thinking, how do you put it in descending? Don't say, sir, I will go to Microsoft Excel and he will do it for me. There is no Microsoft Excel. Okay. What will you do if millions and millions of numbers are there? Huh? Tripti, Dilip Naidu, Krishna Kumar. Anybody? Huh? What will be the approach? This is basically algorithms and data structures, no? Sorting algorithm. Has anybody studied this? Vaguely remember. Okay, now let me okay. We are not able to see now in that. Okay, let's see. Let's go back to. Okay, so 8, 23, 13, 5, 29, 37, 56, 2, 98, and 42. I come again. 8, 23, 13, 5, 29, 37, 56, 2, 98, and 42. Now let us say instead of descending order, I want to put it in ascending order. So what I will do is, first I will assume that 8 is the lowest number. So that is the way the computer science people work. 8 is the lowest number. So it is at the left side. Now I have to compare with other numbers, and then all the numbers which are smaller than 8 will be pushed to the left of 8, all the numbers which are greater than 8 will be pushed to the right of 8. Okay. So what I will now do is, first I will compare 8 and 23. 8, the position of 8 is all right. I'll compare 8 and 13. The position of 8 is all right. I'll compare 8 and 5. Now 5 is smaller than 8, therefore the position is not all right. 8 and 29, position is all right. 8 and 37, position is all right. 8 and 56, position. Like that, once I do, I'll find out that there's only one violation. 5 should have come to the left of 8. Therefore, now I will resequence the numbers and I will put 5 ahead of 8. I'll put 5, 8, 23. And now what I will do is, the third number was 23 and the fifth number was 5. Now I will interchange these places. Now my number is 5, 8, 13, 23, 29. Now I again take 8 because I assumed I live or die with 8 because I assume that 8 is the lowest number. So next I will start with 8 and then compare with 13, 8, 23. So each time with each iteration, so you can see that numbers smaller than 8 will come to the left of 8. So numbers larger than 8 will come to the left of, come to the right of 8. So I have done this. So can you see this? Can you see this? Is it visible?
Not very clear, sir. But
now
fine.
vaguely?
Yes, sir. Vaguely. Yeah.
Vaguely. Okay. Right. Okay. So I think it's 5:30. We'll cover any doubts, any feedback. So you're saying that the board is not okay. So next class I'll fix the board. Audio, video, or otherwise okay. The presentation, font size, everything is all right. Any feedback?
So audio breaks in between sometimes.
Audio
when you
breaks in
speak.
between.
Is all right. Voice also is all right.
All right. Okay. So, okay. So at least the first class was not a disaster. Normally the. All right. So thank you very much. Girish, what do you want to do now? So you people want to register or something because it is not a credit course for credits and all that. I just want to know who are all attending and all that. Girish, can we do something?
Yes.
What can we? Huh? So we will circulate. You got the mail, right? All of you got. We'll circulate this thing so you can fill up an Excel sheet or something. All right. So we'll do something. So I'll do some data science. Huh? So we should do something and figure out who are all attending the class. Okay. So shall we sign off?
Yes, sir.
All right. So have a
Thank
nice
you very
evening.
much, sir.
Thank you.
Thank you very much.
Thank you, sir. Thank you, sir. Thank you.
Thank you,
Okay.
sir.
Thank you. So nice of you.
Thank you, sir.
Thank you. We'll meet next Tuesday.
Yes.
Thank you, sir.
Thank you.